Oh. And we are recording this session for later listening as well, who is working under the supervision of Dr. Chen Feng in UBC Okanagan School of Engineering. So Mohammad Jalalzai is a postdoctoral researcher with us, and he received his master's degree in computer science from the Technical University of Berlin in 2010, and his PhD from Louisiana State University, LSU, in 2019. His research is mainly focused on distributed systems, more specifically on designing, implementing, and testing secure, efficient, and scalable Byzantine Fault Tolerant consensus algorithms for blockchain networks. And he's also interested in the intersection of machine learning and cybersecurity. So this talk will focus on his work on scalable BFT consensus algorithms. And so without further ado, Mohammad, I'm going to turn it over to you to talk about the research you've been doing during your time here with blockchain at UBC. So over to you.
Thank you, Dr. Vicky. Thank you for your introduction. Hi, everyone. Today, our talk is about efficient consensus in the era of blockchain. And I'm introducing one of our works that I have done here at UBC. It's called Hermes BFT, Hermes Byzantine Fault Tolerant Protocol. This is a joint work with Dr. Feng, Dr. Costas, and Golden from LSU, and Janu here at UBC. Coming on to introducing blockchain, we know it's a data structure. It's a linked list of blocks where each block contains transaction and a hash to the and a hash that acts as pointer to the previous block. And these blocks are built based on the consensus. So in order to add a block to the chain, nodes have to go through a consensus process. There are multiple types of consensus processes, like proof of work, which is highly scalable. That means thousands of nodes can join the network, but it's very slow and inefficient. On the other side, there are Byzantine Fault Tolerant protocols that are very efficient, but they are not as scalable. The number of replicas or nodes in the network are very small. If we increase the number of nodes, it basically stops functioning. Byzantine Fault Tolerant protocol, one of the advantages that we have with the BFD protocols, these protocols have been, this research community have been working on these protocols since 1980s, and it's a very famous problem of a Byzantine journals, which is how to coordinate and coordinately or take a action or form a consensus before taking an action, because if there is no coordination, the action might fail. It's based on famous Byzantine journals problem, where if a journals coordinate, they will succeed in an attack, and if they don't coordinate, they might lose the battle. The main part that we have chosen Byzantine Fault Tolerant protocol, that is, it's highly mature, and then we try to improve its scalability and performance so that blockchains can be built over the top of the Byzantine Fault Tolerant protocols. So as we discussed, Byzantine Fault Tolerant protocols have low energy consumption. They usually use broadcast. Their scalability is relatively smaller. There's the typical Byzantine Fault Tolerant protocols have tested with 10 to 20 nodes. And if you increase the number of nodes, the performance degrades. So the challenges that we have in Byzantine fault tolerant protocols are quadratic message complexity. When you increase the number of nodes in the network, the number of messages increases. And then this causes bottleneck in your connection. And at the same time, when you have greater number of messages, you have to process them. So it also costs you additional processing time. There is also higher latency. Some protocols have addressed the message complexity, but then they sacrifice the latency. And when the case of any use case of blockchain, the block sizes are much larger than it used to be. So in Byzantine fault tolerant protocols earlier, before blockchain, these requests were batched together in a small size sort of packets and broadcasted to the network. But now in the blockchain, we are increasing the block size, and block size are like range from 1 megabyte to 4 or 5 megabytes. So this causes the primary node or the replica that broadcasts the blocks to the whole network. This causes a bottleneck for the replica. And this is one of the main problem that we are trying to address. And this problem have not been addressed before. There are examples of some previous work that have tried to address the message complexity or latency or but most of them, all of them actually, they either try to address message complexity or latency. So no protocol so far have addressed the bottleneck in the primary replica. And that's why we have come with the design of the Hermes Bfd. So we have 4 design goals in this protocol. The first design goal is that we want to have a high performance despite slack primary. Slack primary is the primary or the replica that has lower bandwidth, but this primary has to broadcast the block to the whole network. So if it has a lower bandwidth, then it will take a lot of time for this primary to broadcast the block to the network. The second design goal that we want to achieve is that optimistic responsiveness, efficient optimistic responsiveness. So the goal here is that the block have to be distributed in the network and with the speed of the fast nodes. That means our network should operate based on the bandwidth capacity of our fast replicas or fast nodes in the network, not the slow node. So we are trying to minimize the effect of the slow or slack nodes in the network. We also want to achieve lower latency. Latency is also one of the most important performance metric and consensus protocols. It's the time taken by a transaction to get approved. So we don't want our clients to wait longer time for a transaction to get approved. And the last design goal that we want to achieve is a scalability. That means we want our protocol have to be scalable so that more nodes or more replicas can join the network without affecting the performance. The system model is we have n parties or replicas, and the protocol can tolerate up to less than a third Byzantine faults. Byzantine faults can be any arbitrary faults. The network is fully connected and partially synchronous. And we also, our protocol can support up to 1/3, less than 1/3 slack node or slow nodes. So up to 1/3 of our nodes in the network can be slow, can have less bandwidth. And we also assume that adversaries cannot forge on-the-spot these messages because of signature, so they cannot basically break the signatures or hashes. So now we are trying to explain the problem a bit and more in the detail. So the performance of the Bfd protocols are highly dependent on the primary, because if the primary doesn't propose anything, the network cannot move forward. The network cannot do anything. So if it takes longer time for primary to disseminate or broadcast a block, the network is basically doing nothing, and the network is just blocked. And if we have noticed that the bandwidth of the upload bandwidth of our networks is usually much lower than the download bandwidth. Most of these bandwidths that are advertised in our ISPs, they are download bandwidth. They are not upload bandwidth. Upload bandwidth is many times less than the download bandwidth. So usually you have like 4 megabyte of upload bandwidth, or maybe 8 or 10 megabyte of upload bandwidth, whereas your download bandwidth might be many more times larger than that. So for a primary to broadcast a block or to upload a block, its upload bandwidth is much important. And then, but we have much less upload bandwidth. So therefore, the network is blocked, and then this causes additional latency in the network and degradation in the primary. So our aim is to improve this. Hermes addresses this problem, but then Hermes also relaxes some of the safety guarantees, which we will talk about it later. But we also show that this relaxation of the safety guarantees does not affect the safety, actually. And therefore, the safety of the Hermes protocol is similar or equivalent to the other Bfd protocols. So now we come to we want to discuss the first, how we achieve the first design goal, which is high performance despite slack primary. Slack primary is the primary that have low bandwidth. So if you see the diagram here, the pre-proposal and the in the prepare phase, the primary just have to broadcast the block to the subset of the replicas. So the primary does not have to propose a block to every node in the network. It just proposes it to a subset. And when the size of network increases, when the size of the n becomes larger, this subset has to be just log of n, which is very, very small. So then even a slower primary can broadcast to a subset, to a few nodes, much efficiently. So in this way, the performance, the network incurs very low latency. And the other aspect of it is that in order for the primary to propose a next block, it just needs to receive more than half signatures from this subset. So a normal Byzantine Fault Tolerant protocol, if a primary broadcasts a block, it has to wait for all of the replicas, or majority of them, that is 2/3, to receive their signature and then propose a next block. But in our case, the primary just has to wait for a subset of more than half of this subset. So this set is very small. In this case, the primary has to wait very little and then propose the next block. So this increases our block propagation rate. and the primary is able to deliver the block to the network at a much faster pace. Similarly, when the primary proposes a block to the subset, there is a small round of agreement, small communication between this subset, and then this subset broadcasts that block to the whole network. So if a primary proposes a block to this subset, and this subset there with the very high probability, there is one prompt node. Prompt node is a node or a replica that have high bandwidth that can transmit or broadcast this block to the to the whole network. So in this way, our block is propagated into the network with the speed of the fast nodes. This minimizes the effect of slow replicas in the network. So the other replicas in this subset or in this committee here, they will also broadcast the block, but the faster node had already broadcasted. So the network have already received the block and they can take action on it. And then the third design goal is the scalability. Since the message is being exchanged between the subset committee, sometimes also called root committee C, and then the whole network N, the message complexity is order of Cn. It's not order of n squared. So the message complexity is much lower than the generic Byzantine Fault Tolerant protocol. So the lower the message complexity, the higher the scalability. We can add more nodes in the network. It won't affect the performance a lot. And then our next design goal is latency. As I earlier said, we don't want our clients to wait for a very long time to make sure that their transaction is committed. So if you consider Bitcoin or Ethereum, it takes few minutes to even an hour or more than that to confirm a transaction. And the Bfd, it's much faster, but we even improved that. How we improved that, I can explain it in this slide. The general Bfd protocol, if we see in general Bfd, we have a prepare phase. This prepare phase is designed to make sure that each request is unique, that the primary does not propose two blocks for the same height. It proposes only one block for a unique block for each height. And the second purpose of this protocol is that if a weave change occurs, if a primary is changed, we are still able to recover the block that has been agreed by majority of honest nodes. But since this weave change is a very rare event, we don't need this broadcast all the time just to prevent a bad thing in a rare event. Because 99.9% primaries do work, and just to avoid an event that is going to happen 0.001%, we don't have to have this expensive broadcast in the first phase of BFD. So what we did, we just do one round of broadcast in this small committee subset. And this saves us a lot of latency and processing and message complexity. But this then it also has its own cost too. We move this recovery phase from normal PBFT operation to the weave change. So our weave change become a bit more complex, but we have efficient normal case operation. That means 99.9% our protocol is very efficient, works way more better than the general normal PBFT. But during a weave change, then we have additional recovery phase to address the recovery of a block. If a block is agreed by majority of honest nodes, then we do an additional recovery phase and our weave change to recover that block. So by introducing additional recovery phase and weave change, we are saving, improving the latency in the normal phase. So this is a kind of trade-off. And the other trade-off due to the improved latency is that we allow the equivocation attack by a Byzantine primary or by a malicious primary to occur. But the other protocols, the previous protocols, just does not allow the Byzantine primary to perform equivocation attack. In equivocation attack, a primary tries to send multiple blocks for the same height. So it tries to generate a fork and then do a double spending attack. So other protocols avoid this. So the primary is not allowed to do that. What we do, we have, for a better performance, we allow the primary to do this attack, but we have made sure that this attack fails. So if the primary does it, it fails, but it will cost the network some delay. In exchange, we get much better latency. So if a primary performs a equivocation attack, there are multiple layers of defense. First, it's detectable, so we can detect it, and the primary can lose if it's proof at stake. If we are running proof of stake protocol, the primary will lose its stake in the network, or the primary can be blacklisted. But even if if the primary perform this attack, it won't succeed. A client will not consider its transaction to be committed. This, the equivocation attack can only succeed if less than majority of honest replicas have committed it. So if less than a majority have committed it, the client do only consider its transaction to be committed if majority is committed. So if less than majority is committed, client doesn't consider it a committed, and the equivocation can take place, but then there's a recovery mechanism that can recover from this attack. It only causes some delay. But if majority of correct replicas have committed it, then equivocation will fail. So to make it short and clear, if equivocation attack take place, it will definitely fail, and we have proved that. So the primary, a Byzantine primary, has no incentive to perform equivocation, because first, it is highly unlikely, because for equivocation, the primary and the small committee have to be malicious. So majority in the small committee and the primary both have to be Byzantine, which is, this probability is very low. Second, it's expensive, because if they do this attack, they will have to be, they will either be blacklisted or they will lose their stake. And third, it's ineffective. That means even if they perform this attack won't cause double spending and it will fail. So based on this, there is no incentive for a Byzantine primary to perform such attacks. And then we did some experiments and compared our protocol with state-of-the-art Bfd protocol that is designed for blockchains called hard stuff. We performed this test on Amazon Cloud using T2 large nodes, and each of these nodes have I think 8 GB of RAM and I think two core processors. And the results that we got is the throughput, as you can see here. We have compared the Hermes and the hard stuff with the two different block sizes, 2 MB and 3 MB. If you can see, initially the hard stuff's throughput is better, so the number of transactions processed by the hard stuff is more than the Hermes. This is due to the reason that the ratio between the committee size, that small committee size, and overall network is large. But when the network size grows, the Hermes catches up, so the throughput of both Hermes and the hard stuff and 2 MB and 3 MB block sizes are similar when network becomes larger. So we have a similar, is comparable, the throughput. And when the primary is prompt, that means when the primary has high bandwidth, our throughput is comparable to the throughput of the hard stuff when the network size is large. And if we see the latency, the time taken by transaction to get committed, then Hermes Bfd outperforms hard stuff. So in latency, the lower is the better. So if we see the hard stuff and both block sizes, 2 MB and 3 MB, the Hermes has outperformed hard stuff. So Hermes latency is better than the hard stuff. And again, this is when the primary is prompt, or when the primary's bandwidth is very high. And now we tested when the throughput, when the primary is slack, or when the primary's bandwidth is low. In this case, the primary bandwidth was around 8 megabytes. We see that the throughput of the Hermes Bfd is almost 5 times better than the hard stuff. So when we introduce a slow primary, the throughput of hard stuff is 4.8 times better than the of the Hermes is 4.8 times better than the hard stuff. Because in the hard stuff, and hard stuff and all other protocols, the primary broadcasts to everyone. And the Hermes, the primary just broadcasts to subset. And similarly, if we see the results, the latency results, we can see that the latency of the Hermes protocol is at most 15 times better than the hard stuff. So when and we tested this with the block size of 1 MB to 2 MB, The reason was when we tried to test with the block size of 3 MB, the network just crashed and the network was unresponsive. So then we had to change the block size to 1 MB and 2 MB, and we see that the block is much faster, much sooner confirmed and the Hermes protocol than the state-of-the-art hot stuff. So this is all from my side, and if anyone has any question, the overall the summary is that we have designed a protocol that not only improves the consensus performance when the primary is slack or have lower bandwidth, but it also improves the throughput, scalability, as well as latency. So we have improved a combination of the performance metrics and the consensus protocol in a single consensus protocol. Thank you. Thank you. And if anyone has any question, yeah, please.
Oh, thanks very much, Mohammad. Sorry, I've got a lot of noise going on in the background here. But thank you very much for your presentation. So we've got the Q&A. So if people want to post questions to the Q&A, then that would be probably the best way to post your questions. Equally, I think you can open up the microphone to Michelle.
Yep. If anyone has a question, they can raise their hand and I can just unmute them so you can.
Yep. Yeah. Yeah. And maybe while we're waiting for people to think about their questions, this obviously, Mohammad, this is part of a larger program of research. So now that you've achieved the results that you've achieved, where do you see this going from here? What are the next steps in this project?
The next steps is that so currently this protocol, the scalability of this protocol is to few hundreds of nodes. So our next aim is to develop a consensus protocol, a Byzantine Fault Tolerant consensus protocol that can scale to tens of thousands and possibly millions of replicas. Mm-hmm. And so there are some protocols that have achieved this this kind of scalability, but they are not responsive. Responsiveness is one of the characters of Byzantine Fault Tolerant protocol, in which the protocol can operate in the speed of wire instead of maximum latency in the network. That means that these protocols are very, very fast. If you consider Bitcoin is not responsive. You have to wait for some time to make sure with high probability your block is committed. So you wait for some time, but in responsive protocols, you don't wait for a time. You just receive some threshold of votes, and then you know that the block is committed. So it's much, much faster. So our aim is now to design a highly scalable protocol that can tolerate tens of thousands of hundreds of thousands of nodes, but it should also keep responsiveness, which is a challenge.
Mm-hmm. Yeah, absolutely. So for that you need a high computing and
yes,
capabilities. So we will work on that. So does anyone have any questions they would like? I'm not seeing anything in the Q&A. Yeah, so here's one. You said Hermes assumes that network is synchronous. How can you use Hermes over the internet, which is an asynchronous network? Good question.
It's a partially synchronous. It's not the pure synchronous. So partially synchronous protocols do operate our asynchronous network, and then we use some timeouts. And we use timeout only while the primary broadcasts are blocked, and if within some specific time a replica does not receive a block, then they initiate a weave change process, and then choose another primary and another subcommittee. So it's not a synchronous, it's partially synchronous. So partially synchronous protocols can operate over our asynchronous network.
And is that true of hot stuff as well? Is it?
Yes. They are also partial. It's also a partial synchronous protocol.
Right.
Yeah.
Right.
Yes. But the only difference in our protocol, one of the major differences in our protocol and other protocols, is that the other protocols have never considered if their primary have a lower bandwidth, which is a realistic case. So in our case, we show that if the primary have a good bandwidth, have a high bandwidth, its performance is comparable, and even its latency is much better than the state-of-the-art protocol. But if the bandwidth is low, we are many times, our protocol operates many times better in terms of performance than the other state-of-the-art protocols.
All right. Are there other questions to Mohammad on this? Interesting. This is a how to scale the. Michelle? Yeah. Okay.
I don't see anyone with their hands raised, but again, like if you have a question, feel free to raise your hand and I can unmute you.
So probably either they have understand everything or nothing.
Oh, wow.
Okay, so if there are no other questions, okay, there's something in the chat. Let's see, one question, please. Yes, Alexander Henschel to all panelists and attendees.
I've unmuted Alexander's mic.
Yeah.
Everyone, can you hear me?
Hello.
Hi, Alex. I think it's yeah.
Hi, Mohammad.
Hi, Alex.
Great. Thank you for the great talk. I was wondering, could you explain a little bit? So your primary first broadcasts to a smaller group of nodes, which then in turn relay the messages to the larger remaining part of the committee. Could you highlight in which way that is different than just utilizing epidemic gossip from the primary? Because in epidemic gossip, the primary would also just contact a small group of nodes, give them the block, and they would then in turn propagate the block further in the network.
Yeah, so it is so I think one of the major difference will be probably the size of the subset that we choose. So when we choose the size of the subset, we always also consider the Byzantine behavior in for the consensus protocol. That means we should have enough replicas there to guarantee that that at least one of them is honest for the liveness, but for the other guarantees of the protocol, more than half of them has to be honest for the safety. So I think in the the epidemic gossip that you mentioned, they only consider the data propagation aspect of it, but not the other effects of it on the consensus. And this committee not only propagates the block to the whole network, but they also do one round of agreement among themselves. So they do a round of agreement, and then they send, and then if more than half of this subcommittee agrees, then this block is propagated to the rest of the network. And at the same time, they also send this quorum certificate of more than half to the primary, so that primary does not have to, so that primary can propose a next block. I don't know if I have been.
Yeah, thank you. That makes a lot of sense. Thank you.
Thank you.
Okay, any other questions? If you're not able to raise your hand, you can also type in the chat and I'll just unmute you if there's any more questions.
Okay, if no other questions at this time, then I'd just like to thank Mohammad for presenting his very interesting research. And if you have feedback from Mohammad, I think your contact details are available. And you can email Mohammad to gather some more information about the research. And I think you are going to be presenting a paper on this, Mohammad?
Yes.
Yeah. And
the
where
paper,
are you going to be presenting?
Well, it's currently under review, so.
Under review, yeah.
Yeah.
So, so we'll stay tuned for that, and you can dig down into some more of the details in the forthcoming paper.
Yeah, I will be uploading the paper in archive probably in the next couple of days. So yeah, so they can, if anyone wants to take a look at it, then yeah, they can look at it.
Yes. Yeah. So unless there are some more questions, then we will wrap up. I think we have one more monthly research talk for coming up in July, and then I think we're taking a hiatus until September. Stay tuned for our July monthly research talk. I think we sent out information in our newsletter, but that is going to be I'll be presenting that one, and it's going to be on a self-sovereign health data management blockchain solution. So somewhat different, going up the stack again, more application level presentation. But it's very, very good to see this research going at the core blockchain layer in consensus mechanisms, which we continue to be challenged around scalability, and particularly around scalability and consensus mechanisms that's used very frequently in permissioned, private permissioned blockchains as opposed to the public permissionless. So very important work, Mohammad, and I'm very grateful for you for taking your time to present on this really important research to us today. So unless any more questions from the participants today, we will end it there.
Yeah, thank you.
Thank you, Mohammad.
Thank you, Mohammad. Thanks very much. Okay. All right.
Thanks, everyone. Bye.
Thank you, everyone. Have a good day. Bye-bye.